Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you to the public defense of Sarah Gebruers. Sarah Gebruers has presented to the faculty her PhD thesis on the topic Combining Spectroscopic and Astroseismic Modeling Tools for Ensembles of BAF type stars, in partial fulfillment of the requirements of the degree of PhD in Science, Astronomy and Astrophysics. Sarah shall now defend her PhD thesis publicly. Sarah, you're invited to give a presentation about your work for 45 minutes, as I think you've prepared. And afterwards, the examination committee will ask questions. So let me also first introduce to you the examination committee. So on my right, I have Joris van de Vondel from the physics department. And we have Connie Aerts from the physics department as well, who is a promoter for this thesis. And then Andrew Tkachenko, who is also promoter for this thesis, also from the physics department. Myself, I'm Tom van Doorselaere from the mathematics department. And then there are 3 jury members who could not be here, but who are present online and have been there in the private defense. This is Maria Bergeman, she will be present today. Krešimir Pavlovsky from the University of Zagreb. And then there's Joris de Ridder, also from the physics department, who is a jury member. A third supervisor is Hans-Walter Rix, who could not join us today. So please, Sarah, go ahead, and I'll now give you the floor.
Yeah. Okay. Can you hear me? Yes? Okay. So first of all, thank you all for being here today, and thanks for joining online, for those who are online. So today I'm going to present a bit like the work that I've been doing the past 4 years during my PhD. That involved a bit of spectroscopy, a bit of astroseismology, and as my title says, also about the combination of these 2 techniques for ensembles of B, A, and F-type stars. Now, for many of you, like a lot of the words in this title don't really mean anything. You don't really understand what they are. And I hope that by the end of this presentation, you will have a little idea of what everything is. So start very simple with what is a star? So if you are lucky enough to find a dark spot here in Belgium where you can look at the sky in the night, you are able to observe all these little shiny dots. Well, all of these things are stars. They are 3-dimensional balls of gas that produce light. And so in the core of these stars, there is a nuclear source that creates energy. It's a nuclear fusion process. And these are all small particles, hydrogen particles, for example, that if their temperature is high enough, they come together and they fuse together into heavier particles, such as helium. And this produces a lot of energy. And this energy has to go somewhere. It cannot just stay in the core. So it's transported outwards. And that has 2 very important effects. One effect is that there is a pressure gradient outwards, so that the gravitational force is counterbalanced and the star does not just implode upon itself, but it is a ball. We can observe it, and it's in equilibrium. Another important effect is that there are like photons that are produced in this core that are transported outwards with this energy mechanism. And if they can escape the star, that means that we can observe them. We see the light of the stars here on Earth. Stellar evolution. So stars, they live a certain life. The stars that I'm gonna talk to you about today, they are formed in star-forming nebula. These are large clouds of molecules where heavy particles start to clump together and they form larger particles and they will attract more elements and they will become bigger and bigger and bigger until we have a protostar. And as I said, once the temperature is hot enough in this core, fusion processes can take place. And the first fusion process that happens is the process that converts hydrogen atoms into helium. And this can go on for a very long time. This phase is called the main sequence, and it is the longest phase of a star. It can go on for billions of years. And then after a certain amount of time, all the hydrogen in the core is gone. It's all converted into helium. And the only thing the star can do at that point is collapse, because the only force that there is present is gravitational force. So the core of the star starts collapsing. As a reaction, the envelope then expands. You get a star that we call a red giant. That once then the temperature becomes hot enough again in the core, and a different fusion process can take place. Helium can be converted into carbon, can get oxygen. It all depends a bit on the mass, all the cycles are that the star goes through. But in the end, the star ends its life with a planetary nebula phase. The outer layers are expelled into the universe. We get these very beautiful pictures, and what remains is this core of carbon and oxygen that is not hot enough to burn anymore. It cannot convert into heavier particles. It just cools down, and we end up with something that is called a white dwarf. Come in, please. So we astronomers, we don't just look at these pretty picture of stellar evolution because it's not very practical for us, but we plot the evolution of stars in something that is called a Hertzsprung-Russell diagram. That's a diagram shown here on the left of the slides, where we plot the temperature on the horizontal axis, and we point our arrow in the wrong direction because that's something that we like to do. And we have, so the hotter the blue stars on the left-hand side, and the colder red stars on the right-hand side of this plot. On the vertical axis, we have the brightness of the star, so how bright it shines, with the brighter stars on the top. And you see that many of these stars, they clump together on this diagonal, and this is the main sequence. So that's where stars spend their main sequence phase. Then they can go up, become red giants, and they end their life as white dwarfs, cooling down on the left part below that. Now, we don't just classify stars by their temperature, but we also give them a certain name based on their temperature. We're going from O to M, where O are the hot stars, M the cold stars. Why am I telling you this? Because as you saw in my title, I am looking at B, A, and F-type stars. So those are stars that are quite hot already. They have masses between 1.2 and 9 times the mass of our sun, temperatures between 6,700 22,000 Kelvin. And also important, I'm also only looking at stars in their main sequence phase. So these stars internally, they look a little bit like the plot here on the left. So in the inside, we have the core where hydrogen is converted into helium. The energy transport in this core happens via convection. So we have large blobs of material that move up, and if they cool down, they move in again, and you get this convective motion going on in the core. But these blobs of material, they don't just stop at the boundary of the core, but they overshoot a little bit in the region surrounding it. And that's called the overshooting zone.
The slides online are not switching to the next. It's still on the title.
Really? Okay. Well, something had to go wrong, right? Okay.
And next slide, this picks up. Okay.
Okay. So I was saying, so we have the core where convection is taking place, but these convective motions, they don't just stop at the boundary of the core. They can overshoot a little bit in the region surrounding it. And that's like the a bit lighter shaded blue. This is called the overshooting zone. And really on the outside of the star, we have the envelope. And in this part, the energy is transported via radiation. If you now take a 1D slice through it, so if you go from the core to the surface, we can look at the mixing in these different parts. So we have on the left-hand side the core, where there is a lot of mixing in the core. Then we have this overshooting zone where the mixing drops outwards, and then the envelope where there is again some mixing here. What I want to draw your attention to is like these ugly denotations of these mixing regions. So we have FOV, that's the how we call the mixing in the overshooting region, and we have log D mix in the envelope. So these words, well, these names are going to come back later, so you know a bit what this is. And we're also looking at this log D0 value. That's the point where the mixing in the overshooting region goes into the envelope region, so the level of mixing there. So going back to this Hertzsprung-Russell diagram, if we now only look at the main sequence, then we can plot the evolution of a star during its main sequence like this. So it starts on the left, and it goes all the way up to the right. And that's for most of the stars looks a bit like this. For different masses, it will be shifted a bit diagonally, as I showed you before, like these main sequence stars are on the diagonal, but it's all a bit like this. So you would think if I measure the temperature of a star, its brightness, I can put the dots on this diagram and I know the mass of the star. However, it is not as simple as that, because there are other things taking place. As I said, there can be mixing in a star, like this overshooting mixing, envelope mixing, and this can actually add material to the core. So if there's hydrogen in the envelope, hydrogen can be pulled into the core, which means there is more hydrogen that can be burned, so the star lives longer, and you see that the track of the evolutionary track of the star is extended. Additionally, the metallicity of the star, this is all elements heavier than hydrogen and helium, we group them together in a term called metallicity. And so if there are more metals present in the star, these tracks will also shift. So it's not really a one-to-one correlation. These processes are very degenerate with each other. We don't really know what mixing processes are going on. So it's a pretty difficult subject. So why do we study stars now? As I said, we want to know these mixing processes. We don't really get what they are. We don't know ages of stars, rotation, masses. We want to know how stars live their life and how their internal structure looks like. And at the moment, we have a bit of an idea, but we don't know everything yet. And it's also important in other fields of astronomy. Like if you go to study galaxies, you're actually studying large populations of stars. So it's important to first know how these stars live their life, how their structure is, before you can actually start looking at whole galaxies of them. Similarly, if you want to look at exoplanets, which are planets around stars that are not our sun, you also need to know the characteristics of the star itself before you can go study the exoplanets. How do we study stars? Well, in theory, it's pretty simple. You have a real star, and we can, from our theory, make a model for a star with a certain mass, a certain age, metallicity, mixing values. And what we do is we just compare the two with each other, and we see, do they match or not? And where do we maybe need to improve our theory? Where are we going wrong? And we try to calibrate our theory based on our observations until we get a good match with each other. There are various ways in which we can obtain observations of stars, and I'm going to explain two of them to you. First one of them is spectroscopy, and that's something you should all know. If you are outside on a bright day, the sun is shining, but suddenly there is a cloud coming in, and you get raindrops, and the light from the sun is being diffracted, is split into all its colors due to the rainbow, due to the raindrops, and you get to see a rainbow. So these raindrops, they're all little prisms that split the light into all of their colors. Well, what we do is something pretty similar to that. So we observe stars with our telescopes, and then we have an instrument that we call a spectrograph, which is actually a fancy prism, and it splits the light from the star into all its colors. But a star also has an atmosphere around it, like the outer layer of the star, and there are various particles present, atoms, and they absorb some parts of the light, and they block certain things so that they cannot come to us. For example, if you have an atom in the atmosphere of a star, and there is certain, there's light coming to the atom, there is an electron in one orbital, and it needs a certain amount of energy to jump to the next orbital, which it really wants to do. In this case, for example, it needs the energy of the red arrow, the red part of the light, to jump to the next orbital, which means that if we look at this atom, the red part of the light disappears for us. And that would give us like a black line in the red part of the spectrum. And so for different elements, the position where these lines are in the spectrum is different. So if you look, for example, at hydrogen, you see there is a line in the red, in the green, blue, and the violet a little bit. And so by just looking at the spectrum of a star, looking at where these lines are, we can actually infer which elements are present in the atmospheres of stars. Now, we don't look at these rainbow thingies because that's a bit impractical. What we do is we look at the spectrum on the bottom here, where we have, instead of the colors, we have the wavelength. And on the y-axis, we have the flux, like the amount of light in that part of the spectrum that is reaching us. So where there are black lines, you will have dips in the spectrum. And so we can as I said, infer which elements are present in this atmosphere of a star, but we can also infer the general conditions of the atmosphere. So, for example, here you see the temperature of the star. Like, you have plotted various spectra with different temperatures, and you see that the lines, the shape of the line, the depth of the core of the line, it all changes with the temperature of the star. Similarly, the gravity at the surface of a star also affects the width of the lines, and the metallicity. So, all elements heavier than hydrogen and helium, they also if the metallicity is higher, there are more metals present, the lines will be deeper than for a lower metallicity star. We can also infer the rotation of the surface of the star, how fast it rotates, and the microturbulence, so small motions in the atmospheres of the star. And so we do that with a technique called spectral synthesis. So from our theory, we can compute models. So we compute model spectra for various temperature values, various surface gravities, and we create a whole grid of that with all possible combinations of these parameters. And then we have our observed spectrum, and we just compare our observed spectrum to each one of these spectra in the model grid, and we see which one matches best, and that will give us the temperature and surface gravity of our star. However, I'm lying a bit to you, because an observed spectrum does not look like this, but it looks more like something like this. So it has a certain shape in its in the spectrum, and that's a bit annoying because we cannot really compare these two with each other anymore. The shape is the response function of the spectrum, so it's caused by the instrument, by the spectrograph with which we are observing the star. It changes over time. It's really difficult to characterize this, but we need to get it out somehow. And for that, we use a technique called normalization, and that works a bit like this. So assume you have this spectrum. What an observer does is selects points in the continuum of the spectrum, so where the observer thinks there are no lines present in the spectrum. So you take some points, you plot a polynomial through these points, you divide the spectrum by the polynomial, and you get something that looks like this. However, if you look at the spectrum and you look at the two dots that are closest to the big line, you might think like, maybe they are still part of the line. Should I actually include them or not? So we could also try not including them and do something like this. And you end up with a different spectrum. So these two, well, my drawing skills are not that great as well, but you see clearly that they are a bit different from each other. And as I showed before, temperature, surface gravity, all these parameters, we infer them based on the width of these lines, the depth of these lines, but our normalization actually affects the shape of these lines. So it's a complicated process, like one thing depends on the other. And like manual normalization is very, very difficult. So that's why during my PhD, we've looked at an automated method, which we call zeta pane. And in this method, we represent this shape of the function, this response function, by a polynomial with 25 coefficients. And we fit these coefficients simultaneously with all these surface parameters. So that in the end, we end up with the best surface parameters and the best response function for our observation. Another nice thing about zeta pane is that we don't work with this discrete model grid anymore, but we have trained a neural network on this grid, such that we have some continuous spectrum interpolator, and we can just say, like, for any combination of these 5 parameters, give me a model spectrum, and then we can compare it to observations, and it goes much, much faster than before. And so we apply this to a lot of stars, so these are all different stars. And what I plot here is the metallicity that I've inferred with zeta pane versus the metallicity that was determined in literature, where people used manual normalization. And so if the metallicity would have been the same, all these symbols should have been 0, but they're clearly not. And that's, again, this effect of normalization. So here, for one of these stars, I've plotted a normalized spectrum where it's once normalized with zeta pane and once manually. And you clearly see that the depth of these peaks is really affected. And so we infer different metallicities from these two things. Just by looking at these plots, by doing this study, we can't really say like which of these normalizations is better. We cannot go to the star and ask it, like, what is your metallicity? It doesn't work. But one thing that we can do is be consistent. So if we look at the whole sample of stars, we should just use the same technique. And that's why I think that the automated manner is better, because if I would give all of you a spectrum to normalize it, I would get like 50 different results. And so by doing our zeta pane method, we will get the same results each time over and over, and we can just compare things within our sample of stars. So nice, we have a method with which we can actually observe the atmosphere of stars, and we can get the surface parameters out. So let's go on to the second method I was going to talk to you about, which is called astroseismology. Astroseismology, that is the study of stellar pulsations. So stars, they pulsate, they expand and they contract over time, and they can do that in various modes. So they can just do this, the full star expanding and contracting, or they can do it in some configuration as shown here, where like the red and the blue parts, they are moving in opposite directions over time. The white regions are constant lines on the surface of the star. Stars, they can pulsate in many different combinations of all these modes all together, and it all depends on the internal structure of the star, with which modes they are pulsating. The BAF type stars that we're looking at, they pulsate with gravity modes. So there, the pulsations, they're actually excited by mass elements that inside the star. They have their equilibrium position, but somehow they are moved from their equilibrium position, and they are pulled back by the buoyancy force. And they start oscillating around this position, and that's how we create these waves. For gravity modes, they can only propagate in radiative regions, which means that it's outside of the convective core. They can only propagate in the envelope. But what is very nice with gravity modes, if we can observe them at the surface, we can actually infer information about the region around the core, because they're very sensitive to that. So we can actually look into the star, in the interior of a star. How do we do this? So we observe light curves. Light curves are just the variations of the brightness over time. So it's shown on the top panel. And you see that there are various pulsations present here. So you see various kind of sine waves. Some are very small, some are larger. And what we do is we take a Fourier transform of that. What that is we try to find out which kind of sine waves are all present in this top figure. And then we look at like which period do they have and which amplitude, and we plot that on the diagram here on the bottom. And for gravity modes, there is a very interesting thing. We can create period spacing patterns, and there are these patterns shown here. What that is just you take like the left two periods there, you take the difference between them, and you plot that on the y-axis. And you go on every time, like taking two periods, taking the difference between them, and then you get such a period as is shown here. And we can get a lot of information out of these patterns, as is shown here. So here I plot 3 different panels, and in each panel, there are 3 period spacing patterns present. So these 3 colors are the same pattern, but for a different internal rotation rate of the star. So you see that these patterns, the faster the star internally rotates, the more that this pattern gets tilted. So if we just look at how tilted this pattern is, we can know how fast the star rotates internally. Also, like these 3 panels are the same period spacing pattern, but like for the same star, but at a different age, like different phase of its main sequence. And you see that there are some dips coming into the pattern. So first the star is homogeneous, but then due to these mixing processes, there comes more structure into the star, and these dips form into the pattern. What you can also see is like for the black patterns, I've plotted a line through them, more or less. And the position where it intersects with the y-axis, something that's related to pi naught, which is called the buoyancy radius, and it depends on the internal structure of the star. And so what we do is we have these observed period spacing patterns, and then I do a bit of a simplified way to fit these, because I only fit the trends of the pattern. So I don't really look at the dips that are present there, but I just look at where does it intersect with the y-axis and how tilted is the pattern. And in that way, I can infer this f-rod value, the internal rotation, and the pi naught. So very nice. We have a method, spectroscopy, with which we can infer the surface characteristics of stars. They are related to the mass, the age, metallicity, and mixing values. We also have this other method, astroseismology, which we can look inside the star, get our interior information. We can also look at mass, age, metallicity, and mixing values. But if you do this for the same star, it is often, well, sometimes the case that these results are not the same. They are not comparable. And that's a bit strange because we're actually looking at the same star. We're observing the same light, analyzing it with different techniques, and we get totally different results. And that's a bit worrying. So what I did is I created a method to combine the analyses of these two things together, do it together from the start, and try, well, hope that we have consistent results in the end. And we do that with a Bayesian framework, and for that you need to understand Bayes' law, which is the only equation in my presentation, so no worries. The thing that you have here, like X, are the stellar parameters. So this is the mass, the age, the metallicity, mixing parameters of the star. O are the observations, so our stellar spectrum and a period spacing pattern. On the left-hand side, we have just our results, like how our parameters are correlated with each other. The first term on the right-hand side is the prior information, so that's the information that we have from theory. For example, if you say, like, we're definitely looking at the BA F-type star. I said in the beginning, the mass of these stars is between 1.2 and 9 solar masses, so a 20 solar mass star will not be okay for these kind of stars. That's information we have from theory. Then you have a part where we look at the spectroscopic information and a part where we look at the astroseismic information. Now, in practice, to see how this method works, we're first going to take a step back and imagine that we are somewhere in the mountains. And we want to try to find the highest peak. So what do? Like, let's say we're here, and we just start walking randomly, and we hope that we end up somewhere there. And this is called Markov chain Monte Carlo, which is just a chain of random steps that we take, and we hope we end up there. However, it could also have been that you say, like, oh, on the left-hand side, that looks also like a pretty high mountain. Let's walk that side. And then at a certain point, you're at the top of a mountain. You say, like, I think I'm here. This is the highest peak. But we all know that the highest peak is actually there. So how do we circumvent this? We don't just, you don't just walk alone. You ask all your friends to join with you. You put them somewhere in these mountains, and you let them walk, and you hope that as many as possible end up in the right location. Now, we don't look at this in this 3D-ish view, but we actually imagine that we're looking from the top, and then we cannot see the height anymore, but we just use a color code where the darker regions are the higher mountains, higher part of the mountains, and the lighter regions are like the lower parts. They have a lower probability of being the highest peak. And well, for stars, we're not looking at north-south and east-west, but we're looking at things like mass, for example, and age, because this XC, this is the amount of hydrogen in the core, and we all know during the main sequence, hydrogen decreases, so it's actually a good tracker of the age of the star. Higher hydrogen, younger star; lower hydrogen, older star. And so for each of the points in this plot, what we do to get the color of this point, we say, like, for this mass and age combination, let's predict a synthetic spectrum. We compare that to the observed spectrum, and that's how we get our spectroscopic likelihood value. Also, for this mass and age combination, we create a astroseismic model, which is just like a line in my case, and we compare that to our observed period spacing pattern. And then we also go to our theory, and we say, like, this mass and age combination, is that something that's possible? How possible or probable is it? And then we get a prior value. And we just sum all of these up to get the posterior value, and that gives the color to the point in this plot here. We're not only looking at mass and age, but we also have these other parameters, the metallicity and this FOV and log D0 values, if you still remember. And we can get distributions that look a bit like this. On the diagonal, we have histograms. So that's just the amount of these walkers, of these persons, that ended up at a certain mass value, for example, if you look at the left top plot. And then we just look, where did most of our walkers end up? Well, that's the mass we infer for our star. And it's very nice if we just, for this best mass and the best age value, we create a synthetic spectrum, a synthetic period spacing value, and we compare that to our observations. You see our fits, they look pretty decent, right? But there is one small problem. If you look again at this plot, I'm not sure if it's very visible, and like you try to see look at the uncertainties that we get on these parameter values, they are very, very small. They're much smaller than we would have expected. If you would like do a spectroscopic study alone or an astroseismic study alone, you get pretty decent values, but they're never as small as this. So that's really not what we expect. And it took us a while to find out what is causing this. And that's because we are only including statistical uncertainties. We're only looking at the uncertainties on our observations, and we're totally ignoring the fact that our models are also pretty uncertain. We don't really know all the physics in our models. As I said, the period spacing patterns, I'm just fitting them with a straight line. It definitely does not include all the physics that we can. And this should somehow be included. Now, it's very tricky. I tried various different things, but I always bumped upon this problem as well, which is the fact that our spectroscopic and astroseismic observations are really not in balance. Such a spectrum, it contains like 10,000, 50,000 data points, while our astroseismic period spacing pattern, 10-ish, maybe 20, 30. So they are very different in magnitude, and that means that if we compute the spectroscopic likelihoods, it will completely outweigh the astroseismic one. If I would do the analysis where I include both spectroscopy and astroseismology, or I would do an analysis where I only do the spectroscopy, I would end up with the same result. And that's a bit worrying. It's pretty difficult to figure out how we can actually bring them in balance. We have some ideas that might be explored in the future. For example, instead of working with these period spacing patterns, we could actually start looking at the light curves, so the brightness variations over time, or we could go to these amplitude spectra. We could try that, because then we might have like similar amount of data points for spectroscopy and astroseismology. One of the other things, as I said, we have to include much more physics in our models. So for the period spacing patterns, we could try to compute patterns where we do include physics that mimic the dips in these patterns, so we can have a more inclusive model. And one of the other things that we also should do, at the moment, we're just using models where our overshooting in the star, you saw that this FOV thing was just a decreasing profile, but there are many different ways in which we can actually do this. And we should look at various ways in which to create model grids, and in that way we can kind of estimate these systematic uncertainties a bit better and get better results in the end. And then it would also be very nice if we could apply this Bayesian framework to a large sample of BAF-type stars with gravity mode pulsations, so that we can look if indeed we are getting better, more consistent results with our Bayesian framework than by doing the spectroscopic or astroseismic study alone. And so with that, I am at my summary slide. So I hope that I have explained to you a little bit what spectroscopy is now. We can get surface information from stars with spectroscopy. I've talked a bit about the astroseismic part, where we get information about the interiors of stars. And I've also explained to you the Bayesian framework that I've created to integrate these two methods with each other. It looks very promising. Our fits are very good, but we get really small uncertainties like that we need to solve again. So by now, I hope that this title means a bit more to you, and I would like to thank you.
Thank you, Sarah. Before we start the questioning, I want to announce to the audience that this is a public defense, and you will have the chance to ask questions later today. So please already start thinking about your own question. But so now, if everything is going well, there should be Maria Bergeman online. Maria, if you can hear me, please go ahead and ask your questions.
Okay. Sarah, thank you so much. It was a very enjoyable and interesting talk. I have a few questions, mostly on the side of physics. So I will start with maybe a more general one. How would you summarize the main advance that you have brought to the field of understanding structure of B-type stars with your work? Maybe in one sentence, because you have presented a lot of different interesting aspects of it. And I'm wondering, how would you see your major results out of all that you discussed?
For BAF type stars, you mean specific?
Yeah.
So one of the things that I would say, but that's not really specific to BAF type stars, is the fact that we have this zeta pane method, with which we can include normalization in our spectroscopic analysis, which makes things much faster and less dependent on the person doing the normalization. And on the other side, with the Bayesian framework, we are integrating the spectroscopic and astroseismic analysis into one, and this is also done in literature for lower mass stars. There is a lot of research already going on there, but what people do there is they convert the full spectrum information in mostly. What they do is they just use the temperature and the surface gravity, like the surface parameters that are determined, and they use that as observables in their Bayesian analysis, which are actually inferred variables instead of working with the real observations, the spectrum, as what I am doing now. But as you see, I also run into some problems doing that. So I think that is a major advantage, because you're really working with the observations themselves and not on, with inferred observables, depending on already the models that are used there.
Okay, great. So, and to follow up on this, so you extensively use models of stellar atmosphere and stellar interiors. How would you assess the major shortcomings of these models? And how close are we to overcoming them in the next years, so that we get more physically accurate estimates of stellar parameters and also the uncertainties by this combined framework?
Yeah. So on the model side, I think spectroscopically we could do a lot better. We're just using LTE models, and so for the higher mass B-type stars, I think non-LTE effects already become quite important. Especially at the moment, I'm also not including abundances in this analysis, but once I start including abundances of various elements, this will also become more and more important to really use non-LTE models. On the other side, the MESA models that I use, the stellar models, I think they're already quite advanced. They're based on all the research that's done here using astroseismology, so they are calibrated on astroseismic observations. So as I said, we are only including one part of the overshooting profile, for example. We could try to create many grids and do the same analysis with these various grids and get a better estimate of the uncertainty. But I think on that side, we're already doing quite fine. Yes.
Okay, thank you. Then if I can ask one more question. So in your thesis, you are trying to understand the physics of stellar interiors using the spectroscopic parameters, including metallicities, but also chemical abundances.
Mm-hmm.
And I'm wondering how to analyze the very fine and small effects of physics of stellar interior, the disentangled from the effects of galactic chemical evolution in the abundance ratios in a given stellar sample. Maybe you could just summarize what your approach is in your work.
Well, at the moment, I have not included that in my work, I think. well, we're looking at, like, for example, results of the CNO cycle, which are just due to the stellar evolution, we get more nitrogen to the surface than the other things, but that's not really effects of, well, it also of course depends on how material is mixed within the star, because otherwise it would not be visible at the surface. So somehow it's like both it's a combination of the evolution of the stars and the mixing process, so the internal structure. I'm actually not completely sure how you could disentangle like the two from each other. Do we even have to also? Could also, like, for the lower mass stars, there is also this atomic diffusion, which also enhances some elements, but that is not or less the case for the higher BA and F type stars, higher mass BA F type stars, BA type stars. I'm sorry. Yeah.
Yeah. Okay, maybe one more question, since we were talking about the methods that we use to interpret the data. Do you think it is possible to construct an empirical model that accounts for all these deficiencies of physical models by using the systematics and the noise patterns that you get from this Bayesian inference, or a semi-empirical model that would be applicable to observations as we have them, at least presently, with all the instrumental limitations and other problems?
So to have some model that includes all of this systematics, so that we can just, if we have a star, we include this systematics and we have larger uncertainty, something like that, you mean?
Yes.
That would be nice if that's possible. I think it's pretty difficult to obtain. It will also really depend on the mass of the star, for example. You will not have the same systematic uncertainties for an F-type star as for a B-type star. You need to know all the things you don't know as well to do this. It would be nice. I'm not sure if it's possible, and yeah, like you can start constructing models with all different free parameters, and like I think you can get thousands of different versions of the same star with different physics in it. If there is time and computational sources to do that, I think that could give you some kind of systematic uncertainty for a certain star. But I'm not sure if that's the best way to go about this.
So just going back to what you mentioned, that sometimes you interestingly find that there are different solutions that you find from spectroscopy and astroseismology. So these inconsistent solutions can only be cured by improving the underlying physics of the models, you're saying.
By what, sorry?
Improving the underlying physics of the models. So
yes.
the underlying physics. Okay.
Yes, I would say so. Because you're looking at the same star, you're inferring the same, like the mass of the same star. It should be the same whether you look at the surface or at the interior of the star. It just depends on the techniques and the models that you're using, and where those are the things we need to improve to make them consistent with each other.
Okay. I'm not sure how much time I have, so Sarah, am I already over time?
Please go ahead. Sarah is enjoying this very much. So.
Oh, okay. All right. Well, then I'll ask one more question. So, do you think that stellar models, the stellar interior models and stellar structure models, are consistent in their nature? Is there a way to test whether they are consistent?
Well, in these stellar models, we also use, so we have all the physics going on in the interior of the star, but we also use certain atmospheres or atmosphere tables to see what the effects are of these models on the surface. And if you use the same models there as what you use in the spectroscopic analysis, then it should be consistent. And now you make me realize that it's not the case in our example.
Okay. Mm-hmm. Okay.
Okay, are these your last questions, Dr. Bergman?
Yes, I think
Okay.
this is my last question for now.
Thank you. Thank you very much for your questions. So the next person to ask questions is Krešimir Pavlovsky from the University of Zagreb, but he could not be here, but he did send his questions to the jury, so they will be relayed by promoter Connie Aerts.
Thank you. I'm not Krešimir, but he did send me 2 questions, Sarah. So these are not my questions, but you should imagine that he's asking them. I will try to improve the English. Okay. So he starts by saying, somebody said that physics is an art. And I really like that statement now after your talk. That's not a question. But I still wanted to mention it like that. He actually said it's an art of approximations. That's what Krešimir is saying. Our advance in understanding stellar structure and evolution highly depends on the choice of approximations that we make. In your thesis, you were dealing both with stellar interiors and stellar atmospheres, right? Thus, I would like to hear your opinion on which physics, the one of the stellar interior or the one of the stellar atmosphere, is the more uncertain one in regard of the approximations that you have used and why.
Oh.
Krešimir is an atmosphere person and I'm an astroseismologist.
Yeah. Who am I gonna insult? I think at the moment, there's on both sides there's things that are missing. Like we have a lot of approximations in the atmospheres. We have we assume one-dimensional stars there. We only use LTE approximations. There's a lot of uncertainty in the atomic data that we're using as well. Our observations are not always perfect. We can have signal-to-noise values that are very difficult, very low and difficult to see features in it. But then on the other side, if we look at the interior, there's so much that we don't know, that we approximate with random parameters, random profiles. This is a difficult question. Can I just say that I think both of them have their flaws?
Okay, you're very diplomatic here. Okay, and then there is a second question. In the introduction of your thesis, you list the chains of nuclear reactions that you use in the interior models. Mainly talking about the CNO cycle. Mm-hmm. Could you please shortly explain why in your BAF type stars, the CNO cycle is dominant over the PP chains?
Well, the temperature in these stars is much, in the cores of these stars, is much higher than in lower mass stars. And so there is a lot of energy produced, and the temperature sensitivity of the CNO cycle is much higher, so it only starts at a higher temperature, but it's then also, I think, much faster somehow. It's easier to just absorb one atom instead of getting one proton instead of getting 4 protons together. So I think once this is possible, that this is much faster at higher temperatures, and that's why CNO cycle will dominate for those higher temperatures.
Okay, and then a few side questions. Which one of the nuclear reactions in the CNO cycle is the bottleneck?
That's the proton capture on nitrogen, which is why there's such a lot of amount of nitrogen that's just stuck there, and we get an overabundance of it.
Yes, correct. And then so the final part of the question has to do with that. So he writes, but you don't have to look up. In section 2.5.2, you discuss the abundance changes of the CNO elements at the surface, right? And so you also say that the mixing processes eventually bring them to the stellar surface. And so what kind of abundance changes do you then expect for these elements?
For carbon, nitrogen, and oxygen. So, well, we expect that nitrogen is obviously overabundant, and carbon and oxygen, I think carbon underabundant and oxygen more or less the same as if there was no mixing present, I think.
And so is that what you observe actually for your stars?
Well, I would like to do that, but the signal-to-noise ratios of my stars were very low, so I didn't really see a lot of the nitrogen lines. It was really difficult to determine them. But yeah, within the uncertainties, yes, I think.
Okay, I think these were the two questions.
Thank you, Connie Aerts. Instead of Professor Pawlowski, the next person to ask questions is Professor Van de Vondel from the physics department. You want to come in front as well? Yes.
Okay, thank you, Sarah. Just to already excuse, I'm from the condensed matter physics section, so definitely there are much more experts in the room here when it comes to stars. So thanks for the very nice presentation. I think it also gave a very nice overview of how the experiments go, what are the problems. But just keeping in mind, let's say, my background, I think there are more experts in the jury related to the stars as stated. So let's come back to a course I give. It's the experimental basic physics course, which is about instrumentation and how to. I still have one question which was not completely satisfactory addressed. So you have the time today. Is you want to rule out, let's say, the impact of the people involved in the experiment. Let's say, because normalization, you give a very nice example, of, let's say, why you should go for this zeta pane approach. But then still, for me, there is still a big question mark on the zeta pane approach. Because it gives the feeling that, okay, then you have one very fixed, and which I understand, and you use the same process, so definitely that is better. But can you still comment? For me, it's confusing or enlighten me why, for example, you go for these particular functions, which are the Chebyshev, let's say, functions, because, for me, it looks a bit like you just have very sharp features, which is related to spectroscopy, and then you have a very broad background. So if I do signal theory in an electrical engineering approach, I would just say, look, I do a Fourier cutoff of all the low frequencies, and I keep the sharp features, because you, as your example also shows, you get a broadening of the features. So why these ones? And then this was triggered by your statement, I think, today as well. That's the second part related to that. You say, look, I compare it then with the normalization. You show a very nice curve of all the stars. But as an experimentalist, if I would say to my students, let's say, show that your way of working is good, I would say, because you mentioned that was explicitly what you stated, is we can, of course, not turn the star, let's say, have control on the star and really know what comes from the star. And this is the pain, I think, for many people here. We are in a lab, so we can turn the star off and on. This is not the case here. But then why then not try to do something like, you cannot turn it on and off, but I would say repeat the experiment. And show, because you have the background, which you say changes in time, then I would say, if it is trustworthy, I would say do it every day of the week. Of course, I'm not sure if this is possible. And convincingly show that it's much more so. Can you comment on that? Is this done? Let's say, is there just more than the comparison?
So, regarding to your first question, like why do we use Chebyshev polynomials? That's just a choice that we made, and it seemed to work fine. we could have chosen different polynomials as well, or different.
But
functions.
did you try? Because can I interfere? You say it works as well is a fairly vague statement. I would say, did you try with different ones? And is there like a physical intuition? I have no idea how the Chebyshev polynomials look. I Googled, but is there some insight? Why?
We did not try, but it's also used in many other works where they do this normalization automatically. There they also use the Chebyshev polynomials. But you're right that we could have used something else and could have looked at the difference. For the other part of your question, we did test this on synthetic spectra, where we induced some response function, but that is also like we induced a response function based on Chebyshev polynomials. So we kind of included this shape already in our function, and then tried to, like, if we use θ on this synthetic spectrum, could we recover the parameters of the synthetic spectrum? And that worked fine, but it's kind of like a bit biased towards the Chebyshev setup. But we also used it on a number of well-studied stars, and we recovered the parameter values that were found in other literature work. So in that way, we benchmarked our methods a little bit. Another thing that we looked at, because I'm saying that we use 25 coefficients, for example, for this Chebyshev polynomial, why not use 10 or 40 or something? But we also, that is something that we did test. Like, let's say if we use 40 for the same spectrum or 10, we did it for like a whole range and try to normalize the spectrum and get parameters out of it. And those values were always, like the uncertainty that we get in that way was always pretty small, much smaller than these internal uncertainties that we found. So that is in itself the Chebyshev polynomials, 25 coefficients is fine. Whether we should use something else, yeah, I don't know. We haven't tested that.
Okay, thank you. And then perhaps a more general question to you. But again, I'm looking with the glasses from a very simple experiment in a lab, which you can change the parameters, which obviously is not, so don't feel, let's say. But still, when it comes to this last chapter, there was the big discussion in the first, let's say, and now the conclusion, if I understood properly, is the error is too small because there are a lot of errors in the model. And then, do you think it's possible now, or are we really hitting a boundary? Because obviously then I hear, oh, let's make the models better. But as an experimentalist, often this means let's make it even more complex. And then we start gaining insight. So can you comment a bit on that? Is there really a push, and how should I see that? How you envision it, for example, it would move forward?
So yes, indeed, we would make our models more complex. Whether that is a good thing? Well, stars are complex things, so probably the way we approximate them is not really the way they are in reality. So more parameters, yes and no. What I personally am also wondering if there is something like in my whole setup, I tried so many different things. If there is something inherently like with these Bayesian methods that we get stuck in some local maximum, and it is more on the programming side of things, on how this method works, that maybe is not what we expect. We could, like, for example, play a bit around with how large the step is that these walkers take in the parameter space, and maybe that would give us like more coverage of the parameter space. But I tried those things, and that was not really the case. So I'm not entirely sure if this is really something like, oh, we need to make our models more complex and get like systematic uncertainties in that way, or whether it's more like on the technical side more there.
Okay, thank you. Perhaps a final question, if I may, then again, from the experimental perspective, because you mentioned, okay, there's the models, and I think you took a delved into the data and what to get the most out of it. But then could you also do it from the experimental side, let's say, because one approach would be to have better experiments, more data, perhaps, let's say, because you have spectroscopy, and then you have, is there more? Or do you have a direction which would be to have better or complementary data, and which data that should be?
There is definitely other information that we could add. One of the things that I also looked at was just using photometric information, but then you end up with like on this balancing thing on this scale where you only have like 5 measurements at most or something. Like if you just look at an SED, the spectral energy density plot, it's just like the amount of flux at a certain passband of the lights. And like things, there are many different instruments. We could get information from the infrared as well, and include that. But then, yeah, you end up with this fact that you have like 10,000 data points with spectroscopy, 10-ish in astroseismology, and like only 5 or so in photometry. And then you have that weighting problem again. What would be interesting in this case is to, if we have, for example, some eclipsing binaries, which are well detached so that they don't influence each other, then we could have some information from the orbital interaction of the 2 binaries that could give us an independent estimate of their masses. So from that, there are different tools like interferometry, but I haven't really looked into all of these separate techniques. I think the binary approach would be the nice one to actually get external information into this picture here.
Okay, thank you, Sarah. We'll stop here. I think there is still plenty of work to do in this field, which I think is also a good, let's say, endpoint of this thesis.
Thank you, Professor Van der Vondel. So the next questions will be from Dr. Joris de Ridder, but he had a medical emergency, so he could not be here, but he's all right. And in any case, he also sent the questions to the other promoter, Andrew Kashenko, who will ask him on his behalf.
Indeed, Sarah, I'm going to ask a few questions on behalf of Joris. But first, he says that he really enjoyed reading your thesis. It was a pleasure. And he says that it illustrates nicely the shift in the tools that observational astronomy is using in the 21st century, that all of a sudden we have to care about statistical methods, machine learning. No idea what those words mean, but that's what he says, okay? And then he says, I do still have some questions, and there comes a list of 65 of them. But I'll do you and Tom a favor by just asking a few, okay? And perhaps I will start with the last one, because it's about uncertain physics. So Yuri says that in figure 4.1, whatever, you outline your approach where you make several simplifications, like no rotation, LT versus non-LT. You make an assumption about mixing land parameter, and etc. What would you advise the next PhD student to tackle first? What is the crudest approximation you make, and why?
So many of them. Well, since you mentioned it, rotation is pretty important for these stars. These BAF type stars, they're like, especially the B type stars, they're already quite fast rotators, and that like changes their the structure of the stars. They're flattened a bit. It will have effects on internal on the internal processes going on. It will also have an effect on the atmosphere, where you have like suddenly gravity darkening that you have to take into account. So maybe including rotation is one of the things that should be added. Yeah. There's so many things that could be done. Like I can list all of them.
So maybe related to that then, Joris writes that for the sun we have differential surface rotation, right? In the sense that there is a latitudinal dependence of the rotation. While for your B stars, you always assume one single value of V sin I. Does that mean that B-type stars do not have differential rotation, or maybe it's not important for B-type stars? And is there any way to check actually if the differential rotation is present from your own data?
So probably they will have a differential rotation, I'd say. Can we check that from my data? I'm actually not sure about it, since you on the spectroscopic side, you're just using the integrated light from the full surface of the star. Like I know that for the sun we have a nice differential profile, but that's because it's so close to us. I don't think for other stars that we have many of those from spectroscopy or astroseismology.
When you observe the sun as a star, right, you also have a spectrum, and there is some inference of differential rotation from that kind of data too. Can you do that for B stars?
Not totally sure, sorry.
Okay, if you look at the average value of V sin I of a B-type star in the sun, or solar type star.
Yeah,
let's
that's
put it like
super
this.
small. Like V sin I, is that right?
Yeah.
Yeah, that's not very high.
For B stars or for sun type stars?
For solar type stars,
Okay.
sorry.
Yeah. Okay. Maybe next question then. For all your spectrum models, you distinguish between macro turbulence and micro turbulence. Does it make any sense? Because Joris's understanding is that turbulence generally has a very broad spectrum of sizes. Do you really have to distinguish, or you just have to model turbulence maybe?
I'm a bit confused because I actually don't really, in my work, I only use V micro, so inherently I'm just including the macro turbulence in the micro turbulence somehow.
Yes, but you discuss it in the thesis, macro turbulence
Yes, I
as well.
discuss it in the thesis.
Does it make any sense to go to two extremes like macro and micro versus just modeling the whole spectrum?
Well, I think they will have a bit different origin. Like you have like this small scale turbulence and this larger scale. And if you want to know the origin of the two of them, I do think it makes sense to differentiate between them. It's also thought that like pulsations can have an effect on them. So I think if we have microturbulence and macro turbulence, that we can infer something from that.
Yeah, I think you're heading in the right direction. Do these parameters, they have any physical meaning, or they're just nuisance parameters?
Well, they are the small velocity fields, so there are physical parameters, right? So yes.
Okay. You have time for more? One more. Oh, now I have to choose one out of 63 remaining. Good. Can you briefly summarize how you derive the uncertainties on the surface abundances, given the fact that you fix the Chebyshev polynomial coefficients and the stellar parameters? How do you propagate the uncertainties into the abundances, if you do it all?
So first of all, what I did is, I ran Zeta-Pane. You get these optimal Chebyshev coefficients. You get surface parameters with a certain uncertainty on them, but only for this certain response function that we determine. But since we have like the response function is determined together with these surface parameters, so the uncertainty on these surface parameters contains some knowledge about the variation in the uncertainty in the response function. And then what we do is we fix the V sin I and metallicity of the star. And then we go to try to determine the abundances of every element, while also varying the temperature, the surface gravity, and the microturbulence within the uncertainties that we derived previously. So in some way, we include part of the uncertainty on the response function in this abundance determination, like that, if that's clear.
It is to me. Okay, thank you.
Thank you, Andrew. On behalf of Joris de Ridder, not you, of course. So you know what the disadvantages of having a chair who is also interested in your work? The chair is also asking questions. So let me ask my first question. Back when I was a student, in 2002, I was in Connie's courses, as Connie remembers very well. It was all about line profile variations. As you've also mentioned in your thesis, line profile variations show up in the spectral data, which you have and which you model. How do you include these line profile variations? How can you get them out of the data? And how can you incorporate them in the modeling?
Okay, so at the moment, we're not including them. We're just ignoring that they're there. What you need for that is to have spectra of the same star over time. And then you will see that these lines, they will vary a little bit. They will shift a little bit due to these pulsations, and they will have like some asymmetries in them. So if you have high resolution spectra, that you can really clearly see all the spectral lines, and you include this various epoch methods, so you look at various epochs at the same time, you can somehow include that in the methods, I think. But you really need good data for that. The data, like in my first chapter, the Hermes data I'm using there, I don't think, especially for the B-type stars, that was not high enough quality to do that.
And what if you take the spectra like an ensemble over, like you take maybe a mean or a median to get the line profile variations over these different spectra you get for the same object? Is that a possibility?
Maybe, but it's also really heavily correlated with all the other effects, like your V sin I, microturbulence. Yeah. Mm-hmm. It will all be heavily correlated, and I think to really disentangle them, high resolution data, and I think like the time component is also important in that case.
Of course, yes.
Yeah.
So I have 3 more questions, but it's also a public defense, as I warned you. So for each question we get from the audience, I will ask 1 question less. Yes, please go ahead.
So I was just wondering, like, I don't know anything about physics. So if you were explaining to me, it would take years. But if you were explaining to one of your colleagues, like one of the other PhD students, how long would it take for them to do this kind of, like, to have a spectrogram and have it converted and everything? Like, does it take half a day to explain, or does it take like 10 minutes?
It will be more than 10 minutes. Probably to get the hang of it, maybe half a day. I don't know. Well, it might be faster, probably. But
Thank you. Any more questions? Yes, please go ahead.
So, in a couple of weeks, I'll be in La Palma with the students, and I know that they will spend the next 6 months usually to normalize spectra. So, I would love to know where to find the Z pain and have the students just run with it immediately, so that they can just do that part of the analysis in a few seconds, hopefully.
Yeah.
I know, Zeta Pay, one of the stars, Zeta Fuchsius, that shows up time and time again. So yeah, I would just love to know, is this on GitHub?
It is on a GitHub, but I'm also planning to clean it up a little bit and have it a bit more structured and have it on my GitHub as well. Yes.
Thank you. Another question? Yes, please go ahead.
So, one like spectra that it shows, like they mostly have a little more basic question about spectra, I guess. So, the spectra all have like lines corresponding to the absorption lines, but shouldn't they also have peaks corresponding to the emission lines?
Some stars can have that. This is mostly the case when there is a disk around the stars, or there is material that is also heated, and then it starts emitting light at certain lines. So that's possible when the material gets ionized and gets like heated up and radiates by itself. But for the stars that I'm looking at in this spectral region, that is not the case. No.
Thank you. And then I see another question in the back. Yeah.
Hi, Sarah.
Hello.
I'm going to ask a technical question, if I may. You said in your one equation that the prior is everything we know about theory. I'm going to disagree with that.
Mm-hmm.
The prior, I would argue, is everything we think we know about theory and everything we think we know about biased observations. So within your prior, what are you doing with the observations? Do you assign anything to anything?
So my prior at the moment is just like, don't go beyond the boundaries of my grid that I computed for BAF type stars. So just mass ranges and everything. And then I also have a prior on like V sin I and F rods so that they don't go above the critical rotation rates. But that's nothing from observations in there, I think, if I get your question.
Ensemble part of your analysis, is there anything to handle sort of biases towards lower mass stars being more common in the universe?
I included that at first, but I removed it again, the initial mass function, because indeed, like it would heavily bias the whole method towards lower mass stars, and it might not be the case. I'm not sure if that's a good prior to include, actually. Maybe if you look at really large samples of stars, but for the moment, it's just 100-ish. So yeah.
Do you think that's the possibly propagation lacking from your, let's phrase that. Do you think that that is possibly why you get very small errors in your final results as well? Because you put a lot of emphasis on the models being wrong, but as an observer, I would also say the observations are probably wrong to some extent as well. Do you fully trust them?
Well, we include uncertainties in our observations, but not in the prior, right? So we have like flux uncertainties on the spectra. We have period uncertainties, but it's all in the in our chi-squared of the likelihood functions, not in the prior information. So I'm not really sure what you're hinting at here.
I'm just wondering if you thought about the ensemble part, if you can include prior information for the actual size of it.
Yeah, there's a lot of uncertainties coming from that as well that is not included at the moment. Like the way how we go from these light curves to this amplitude spectra to the period spacing patterns, there are a lot of choices made in that. And that is not really reflected in the uncertainties that we use at the moment. What? I don't know how that can be included somehow, because I think it also depends a bit on your on the star you're looking at, right? So it will be a case-to-case thing that you will have to include there.
Okay, thank you. Unless there are any burning questions, let's close the question session here, and the jury will retreat and deliberate on the thesis. So, ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee, here present, appointed by for granting the doctoral degree in science, astronomy, and astrophysics. Sarah Gebruers has presented to the faculty her PhD thesis on the topic combining spectroscopic and astroseismic modeling tools for ensembles of BAF-type stars in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And she has defended her thesis in public here today before the examination committee. And the examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Sarah Gebruers the degree of Doctor in Science, Astronomy and Astrophysics. I close the session and congratulate. So please sit down. Sarah, congratulations. I've heard there is some words to be said by your supervisors. Hier nog.
Okay. Dr. Gebruers, welkom in de club van de dokters in de wetenschappen. And I will mainly do this part in English, but let me first of all stress that I have heard many public PhD defenses, many talks, and this was way better than usual. Thank you for that, Sarah. And you have shown us your talent today, right? En ik ga nu overschakelen naar het Nederlands. Zie je wel dat dit doctoraat er zou komen? Hè? Zoals we dat besproken hadden tijdens onze COVID-wandeling onder de meisjes. Dat herinner ik mij. Van harte gefeliciteerd. Maar het is nogthans niet dat je er met volle overtuiging aan begonnen was, vond ik. Want je wist eigenlijk niet zo goed of een doctoraat wel iets voor jou was. Huh? Wel, dat hebben we dan vandaag gezien. Hè? Ja? Je wist ook nog niet zo goed 4 jaar geleden wat je zou gaan doen. En eigenlijk, vandaag, is dat misschien ook nog niet zo heel duidelijk. Huh? Ja? Wat je wel weet, wat je mij verteld hebt, is dat misschien een loopbaan in academia, waar jij de grote leider wordt, niet iets is wat je wil gaan doen. En dat is heel belangrijk om te weten wat je eigenlijk niet wil gaan doen. Dus ook daarvoor eigenlijk proficiat, Sarah. Het is goed dat je dat weet. Hè? En het is tegelijk niet erg dat je niet weet wat je dan wel de komende jaren van je loopbaan gaat doen. Ik heb vandaag veel geleerd daar rond. Ja? Ik heb uit je PhD-boekje geleerd dat jij heel goed aan de slag kunt als schrijver van kinderboeken. Ja? En dat is geen grap, hè? Ik meen het echt. Dat je ook aan de slag kan als tekenaar van kinderverhaaltjes. Ja? En allebei kan ook. Ja? En ik heb ook gezien wat voor talent jij hebt als spreker. Ja? Dus er is heel veel toekomst. En wat origineel, want ik heb nog nooit, maar dan ook nog nooit, een PhD-student gehad die kindertekeningen in haar doctoraat opneemt. En ik vind het geweldig. Ik vind dat echt geweldig. Dus dan vond ik, dat verdient elke... Ik heb dat ik weet het nog niet zo lang dat je dat van plan was. Hè? Dus ik vond dat ik een speciaal cadeau moest gaan zoeken voor jou. En dat heb ik even met Andrew besproken, want hij is eigenlijk jouw echte promotor natuurlijk. Dus hij moest echt wel de goedkeuring geven. Dus ik heb gezocht naar een cadeau van iemand die twijfelt in haar leven, van iemand die een artiest is, van iemand die tekeningen maakt. En ik heb dat effectief gevonden in een jonge artieste, schrijfster eigenlijk, die een boek gemaakt heeft omdat ze zelf niet zo goed weet waar ze naartoe wil. En ze heeft dat prachtig verwerkt in een boek met tekeningen zonder woorden. En de boodschap van dat boek is, vele mensen weten eigenlijk niet zo goed waar ze naartoe willen. En ik vind het prachtig verwerkt, vele verhalen in elkaar geweven. En jouw PhD-boekje deed mij daaraan denken. Dus ik ben dat boek niet alleen gaan kopen, maar ik heb het ook laten signeren. Speciaal voor jou. Heb ik nog nooit gedaan. Dus ik hoop dat je er een boodschap in vindt. Ik hoop dat je mij ook altijd weet te vinden als je iets te zeggen hebt. Hè? En we hebben ook nog wat andere, meer klassieke cadeautjes die je zou moeten doen ontspannen. En vol zelfvertrouwen eigenlijk de toekomst in te kijken. Hè? Geniet van deze dag. Geniet van deze prestatie. Ik vond het een prachtige lezing. Ik wil het nog eens zeggen. En dan geef ik nu het woord aan jouw echte promotor. Proficiat, Sarah.
Hey, Sarah. I'll start in English, and we'll continue in English. So usually people start by congratulating with the title, and that's what I usually do as well. But today is an exception, so I'm gonna, at the risk of jury members being mad at me, I'm gonna review one thing that was just said in the deliberation room. Yeah, it was a fabulous talk. Congratulations on that. Yeah? And now, congratulations. Yeah, on getting the title. Yeah, it's a major milestone, and I'm very happy that you have achieved that milestone for you. Yeah, and you know, you're not the first PhD student to graduate in my career, but you're only the second one who I had the pleasure to see developing from the first year of masters up to now to the title of Doctor in Science. Yeah, I find it very nice, you know. And it's in that first year of masters that I actually learned what an angry Sarah could look like, actually. Yeah, yeah, and yeah, and even though people in the audience sitting here, they probably know you as a always smiling person, as you do now, very friendly, very polite person. I can, guys, assure you that Dr. Sarah Gebruers can defend herself pretty well. Huh? So who knows? Maybe that's the actual reason why at that time your partner in the research project course, who pictured himself as a roadblock on your way, ultimately just quit the academia. Yeah, maybe it's because of that. And, you know, I still remember our discussion with Joris Derrida, who was supposed to be here today, but unfortunately couldn't, in our office after one of the one of your progress meetings with him. Yeah, while it was super obvious to us that you were a very good candidate to start a PhD, we saw that you're still doubting whether or not you want to continue in academia. But at the same time, we knew that you were very passionate about traveling. Yeah, and you know, so astronomy and traveling is somehow combinable if you make an effort, right? And that's actually how Connie came up with an idea of a joint with MPIA in Heidelberg project. And you made it very clear to us at the interview that's the one you want because of travel. Eh? And yeah, now I really want to tell you how sorry I am about the COVID-19 hitting you in that respect. Yeah, we knew how difficult it was for you, how much you suffered. Yeah, and if I would bring an analogy here, I would say it was more like a bird in a cage, yeah, for you. But I can assure that we tried our best to help you to get through that, and I hope that we at least partially succeeded in that. Yeah? En nou, I think quite predictably already, ook een paar woorden in jouw moedertaal. Dus dikke proficiat met een prachtig werk, zo'n prachtig werk dat je hebt gedaan tijdens de laatste 4 jaren. Ja. Nu kan je wel zelf antwoorden of je een geschikte kandidaat was om met PhD te beginnen. Ja. En ook, ik wil ook graag jouw ouders bedanken. Ik geloof dat jullie vandaag alle reden hebben om heel trots te zijn met jullie dochter. Ja? En aan Matthias, hallo Matthias. Huh? Take care of her. Ja? Maar niet vergeten dat ze soms een klein beetje boos kan worden. Huh? Good. Proficiat, Sarah. Well done.
This thing still on? Yes. Okay, so now I'm expected to also say something. I'm really bad at that. Just want to say thank you all for being here. Thanks to my supervisors for the past 4 years, for everything you've done. And I also have some presents for you. I will probably give them afterwards. And I just want to say that there's a reception in the Stu Cafe. And so please enjoy yourselves. Thank you again.